again is with the exam on Wednesday. Uh, Two things. One, I mean, if there are people, if you're coming in and there are people still taking the exams, come on in. Having three different exam sheets, just flip flopping the questions around is a little cumbersome. I'm only going to do two, but just you have to make sure, and I'm going to try to do it in rows and get the exams put out there in rows, so that I'll probably try to get in early and do that, so that you can, you have just as long as you're a different color from the person next to you, side by side rather than front to back's a little harder to be observing somebody else. Not that I'm saying anybody would do that, but again, it's the appearance of impropriety as well as impropriety itself that are significant. So that's the exam dynamic that's there. And once again, if somebody needs a little extra time, I'm sure we could scoot over to the lab uh, at 11 if necessary to do that. So that's the exam announcements that are pertinent. Again, I thank you very much for those people who have been, and all of you should be if you need to, sending me just a couple of quick questions about, clarifying a concept, that type of stuff, et cetera, et cetera. I'm good with that. Today's a busy day, so if you have more questions and I happen to get them this afternoon or this evening, I probably won't get them until tomorrow morning. That kind of stuff. My stepson's coming over to watch the Penguins tonight, rather than have to watch the Steelers again. Don't lash out at your students because you're angry at the defense. It's okay. I took away from my beauty sleep, and Lord knows I need it. Not that funny. People in the front row are laughing at me, not with me, at me. It's nothing compared to the trouble I was in with my wife this weekend. Oh, all right, let's get started. So we left off here, and I'm just going to really do excitation, contraction, coupling. I'll have a brief introduction. I sent you PowerPoints 9B and 9C, a brief introduction to B, where it's a little bit more about actually how muscles and the signals get going. So, but let's start with this. We went over this animation before. I'm going to go over it again and just clarify through it to reinforce it. Okay, excitation, contraction, coupling is just that. We're changing the electrical signal effectively to a mechanical signal. Always, and this is going forward, electrical events precede mechanical events. Electrical events precede chemical events. Electrical events precede mechanical events. They come, and that's sort of the batting order: electrical, chemical, mechanical. Because electrical is the fastest, chemical is the next fastest. Mechanical, even though it doesn't take a lot of time, we're talking in terms of milliseconds, it still takes more time. So that's really sort of the takeoff point for that. And so this is the whole idea when I was trying to demonstrate to you before about the triad. We looked at this animation. So once we reach that action potential, once that signal is broad enough to be able to trigger across that whole muscle fiber, what it does, it transmits along the sarcolemma. That's just all that means. It's that individual muscle fiber's plasma membrane. But it's important, and I'll tell you the same thing I told the other class. One of the questions involves the T tubules. They're extensions of the plasma membrane, whereas those wells, those terminal cisterns, they are really just foldings or enlargements of the sarcoplasmic reticulum. They sound similar, they're not the same. That's part of the smooth endoplasmic reticulum. You need to make note of those, not for this exam, certainly, but for down the road. I don't know when that exam is going to be. It's probably going to be maybe another 2 weeks from about now. Trying to get that in before typically everybody gets pummeled on that last week before the Thanksgiving break. I'm going to try to get it in more toward before that happens. So excitation, contraction, coupling is just that. So it travels along the sarcolemma, which you saw before, and eventually it's going to lead to contraction of the myofilaments. That's what we really look at today. So it's propagated. It means just carried along that waveform, along that sarcolemma, down the T tubules, and it hits basically that signal where they join in the triads, as you might remember from seeing before, and we'll look at it again, it triggers those voltage-gated sensors that allow the calcium stored inside to be basically to pour out of, that's where they're sort of trapped or sequestered is a better term, inside that sarcoplasmic reticulum and flow out into the cell itself. You're going to see the language, and I will explain it. And it's going to lead to the contraction. The action potential is brief and ends before the contraction. Here's the take-home point. For many of you, depending on where, particularly those going into nursing, this is something you really see manifested when you start looking at AP2 and electrocardiograms and things like that. Understand why this is where the importance comes from. For many people, many of my students, they want to work in critical care, emergency room, ICU, pediatric ICU, recovery, OR, blah, 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 blah. If you're going to work at UPMC, unless they change the rules, and I don't think they did, you can't just say, oh, I want to work in the emergency room, show me how to do that and let me work there. It doesn't work that way. You have to be vetted additionally, certified additionally, and you have to know the appropriate like cardiac medications. You have to know interpretation of electrocardiograms. So that's more testing, and you have to do that when you're hired or when you move into that position. So, I mean, and it's a week program. It's intense. This is what they used to do. Maybe they changed it. I mean, you study it's a Monday through Friday, 8 to 5, intense for 8 of those hours with a lunch break, homework every night. On the Friday, you take a comprehensive exam on everything you knew. And if you don't pass it, you can't work in those units. You can work anywhere, but not in a critical care unit unless you can certify that. So I'm trying to prep many of you for this kind of stuff. And it just goes on, whatever field you're in. You're constantly being examined, licensed, vetted, et cetera, et cetera. We all have continuing education is typically part of these things. There. The school thing does not end. It's forever. We say in my own neighborhood, forever. Moving on. So that's the sermon for today, everybody. So here it is. Remember this. It's here. It gets past those voltage-gated sodium, potassium channels. It spreads all over the place if it reaches that arbitrary thing we call threshold. Okay, and it's going to go down along the sarcolemma. That sort of yellowish color is the sarcolemma. Okay, and that's the start of the T-tubule. You can see the triad arrangements that's there. In blue, that's the sarcoplasmic reticulum, the calcium stored in there. It's going to shoot down there, hit those voltage-gated channels. And what you'll see afterwards, and this is what we're going to look at a little more closely today, it's going to take that tropomyosin, that thread-like protein covering the heads, being held in place by the troponin. Once the calcium gets in there, it's going to basically expose the active sites. It's going to allow the tropomyosin thread to move out of the way. The heads are going to be exposed to one another. They're going to join immediately. And what will happen, as you're going to see, and that's really another one of the take-home points, these heads, we call them pre-cocked or preloaded, and they will fire or pivot or move in such a way that they're going to pull the thin filament toward the midline, being pulled because of this ratcheting or pivoting of that loaded head in this direction, pulling them aside. And in so doing, the boundaries of the sarcomeres, those Z-discs, are going to come close together. And so this is what we saw before. Just a quick review of what it is, without doing a whole lot of highlighting. I might narrate over.
Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules.
And these are the individual fibrils,
or T-tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T-tubules make contact with the calcium-storing membranous network known as the sarcoplasmic reticulum, or SR.
Here you see that triad
Where it
relationship.
abuts the T-tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T-tubule plus two adjacent terminal cisternae is known as a triad.
That's important.
The membranes of the T-tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T-tubule, it causes a voltage-sensitive protein to change shape.
It's a voltage-gated calcium
change
channel.
opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fiber.
And you're going to see now, coming up, how that process works. The key part to understand is muscles are ready to fire at all times. When your muscle is relaxed, it's storing energy in those myosin heads. They are being basically loaded, like you're cocking a trigger. If you know what a crossbow is, it's kind of like pulling that, having the bow pulled back and anchored and firing like that. One of the early weapons of war. Effectively, that's what's there. So the muscles will fire. All they need is for the two heads to come in contact. And that will effectively release that trigger and it'll pull it toward there. And it will continue to do so as long as calcium is in the area, keeping that tropomyosin from covering the sites, and as long as there's sufficient ATP to accomplish the process. You need a lot of energy for muscles to fire. We need ATP for that nerve, basically to say to at the neuromuscular junction, okay, boom, I need to cause that action potential for that nerve, basically to say, release the acetylcholine, let's have enough of it, we'll get the threshold, and we'll send that signal. And you just saw before, T-tubules, terminal cisternae, triads, voltage-gated calcium channels, blah, blah. Then the energy is already in the heads. They're pre-cocked, ready to go. To relax the muscle, we have to put more energy in. Two ways. We have to put ATP in there to release and recock it for the next time. So just to release that fiber, we have to put energy into, as you will see. And to recock it, you will see. You will not have to know the intricacies of that. I reserve that for the advanced physiology class. It's a little bit more technical jargon. You just have to know that ATP is the culprit. They're attached. If you don't have more ATP, they stay attached. So it releases that junction point between the active sites on the myosin and on the actin and recock the head. And now we're not done yet. We have to then take more energy in the form of ATP and pump the calcium back in to the sarcoplasmic reticulum to store it, so it's no longer technically in the cell. That's what you're going to see at the PowerPoint that's projecting now, to describe the difference between what is called intracellular and no longer and flooding the cell itself with calcium. That's really important. Oh my gosh, what is she doing? Pardon me for laughing. Oh, the dog's having a bad hair day. He's a dog. He's allowed to. I'll get the picture for you as we're getting ready to leave. Moving on. I have to put up with this. I can't have bad hair days anymore. Not enough hair. The only humor I ever get a response from is self-deprecating. It's okay. The dog gets treated better than I show. Doesn't happen to me. I don't get my hair brushed. Not that funny. The front row in the other class, same problem. You're all in trouble. The rest of you are okay. I can deal with you. Maybe not. moving on. So low intracellular calcium means the calcium is stuck in those storage wells in the sarcoplasmic reticulum. It's technically not in the cell. The tropomyosin is in place. Those threads are covering the active sites. The myosin and can't attach to the axon. Effectively, the muscle, even though it's ready to fire, it's relaxed, just like for you and I. And again, once those voltage sensitive or voltage gated protein channels in the T tubules change shape, the calcium floods the interior, the cytoplasm or cytosol. We call that high or higher intracellular calcium. Once it leaves the wells, now it's technically inside the cell. That's a little confusing, I find, to students. The calcium attaches to the troponin changes its shape and moves the tropomyosin away. Again, whatever analogy works for you. Basically, it's an interaction between proteins altering their position and exposing the heads. I like the one with threads and, push pins, staples, whatever, thumbtacks, anything you want to think of, locking it in place. The myosin heads are then allowed to bind. They can't help it. The sites are next to each other, molecularly apart. Oops. Pardon me, going backwards. Boy, I really went ahead of that one, didn't I? Sorry. And so the myosin heads are then allowed to bind and form the cross bridge, and it begins to cycle. It will continue to form, and you'll see this in the animation, cross bridges. And as long as the calcium is there and as long as there's energy there that's available, it will begin to slowly, and begin to pull those actin filaments closer and closer to the midline, which is as far as they can go to maximal contraction. And in that way, the sarcomere, and indeed all of the sarcomeres, can shorten, and effectively we begin to demonstrate that as a muscle contracting. It doesn't happen right away. It's just like this. If I'm lifting something light, okay, I won't have to use a whole lot of those. I won't have to shorten it a great deal. If I try to lift something much heavier, then I'm going to have to employ that. I'm going to have to go to maximal contractions for all of the individual muscle fibers in that particular muscle to make it work. So when the nervous stimulation ceases, when the signals no longer are coming from my brain by way of the spinal cord to the particular muscle, at that point, more energy. Got to pump the calcium back into the sarcoplasmic reticulum, and I have to detach. That's significant. And we call this whole activity of attaching and attaching and then firing and then detaching and resetting the cross bridge cycle. There's technically four steps that are part of it. You don't have to go crazy about this. The key is it's a high energy myosin head. It's loaded with energy already. There's an ATP effectively sitting on it. So the cross bridge forms, and at that point, they call it a power stroke, a pivot, fire, whatever works for you. And it pivots and pulls the thin filament toward the mid or M line. More energy when the process is either done or we have to engage more and more contraction. The ATP attaches to the myosin head, causing it to detach. Okay, and at that point, not only does it detach, it recocks the head. And they talk about it, and this is where I don't get crazy about energy from hydrolysis of ATP. The ATP essentially binding to it, splitting into its components is what they're talking about. We will not have to, I certainly won't ask you to know all the sort of intimate details about how that process occurs. And that energy from recocking the heads is used for the next step. So they show it to you here. Here you can see they're attaching. Assume now that the calcium is in the area. It's caused the troponin plugs, as I call them, and allowed the heads, the active sites of the heads, to be exposed to the active sites of the myosin. Notice the position. It's angled this way or that way, depending on which side you look at. That's the power stroke. As soon as they attach, boom, begin to pull the actin toward the midline. ATP comes along, detaches it, and then ATP, as you can see, changes. They call it hydrolysis. Don't have to know that. Basically, the ATP first detaches it and then recocks it. And will continue to do so again, as long as there's calcium in the area, keeping those sites exposed. as long as there's sufficient energy until the process effectively ends. And so this is what it will show you here, and I'll review this and go over it in a little more detail.
The contraction of a skeletal muscle generates the force necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads and thick myofilaments form cross bridges with actin molecules and thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1. Cross-bridge formation. The activated myosin head binds to actin, forming a cross-bridge. Inorganic phosphate is released,
That's the part
and
too
the bond
technical.
between myosin and actin becomes stronger. Step 2. The power stroke. ADP is released and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3. Cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4. Reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position. As long as the binding
Very good
sites on
illustration.
actin remain exposed, the cross-bridge cycle will repeat. And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
And so that's the whole picture of this. And to bring it to understand, I mean, this is the parts, all I care about is you understand that ATP had to be used to be released and recock the heads. The fact that it hydrolyzes or losing the inorganic phosphate makes it stronger, and then losing the ADP causes the power stroke, not that vital. To my advanced physics, that's more vital. So, I mean, it's always, every course you take, it's all about the details. And the more detail intensive it is, typically the higher the levels. And if we look at it in a graduate or medical school environment, more intense still. So this is what they're talking about, looking at the individual sarcomere. It's just repeated all over all these literally thousands of sarcomeres throughout. And what we're trying to achieve is this degree of contraction. And that would be maximally contracted. So it might start with just a little, and you'll see when we go to the next PowerPoint sequence how this, it might just be a tiny amount, and we'll have almost infinitesimal, if any, motion occurs. Probably won't get that in thoroughly today. And so now this relationship between the thick myofilaments pulling the thin myofilaments toward the midline. So it starts like that. Again, the troponin is in place. It's holding, as you can see, the active sites on the actin, and then you can see the head is cocked. I'm not worried about the hydrolyzed ATP. Calcium floods. They attach strictly to the troponin. Anything that attaches to a protein or comes in contact with a protein alters its shape. So this complex is effectively what it is. By altering the troponin, it allows the tropomyosin to somehow move and expose those little dot areas on the actin, which are the active sites. What they're pointing to as binding sites in the illustration. Those binding sites they're right there. Again, micrometers, millions of a meter apart. And boom, effectively, once they touch each other, the reaction ensues and it pivots and pulls it closer to the midline, as we were describing. To relax it, ATP has to come to the party, cause it to relax and to recock without going through all the steps. So these are the 4 cycles. So the cross-bridge cycle exists with the calcium coming in, causing the alteration, and then that forms immediately. Again, if we're looking at this picture, you can see the active sites are exposed, the tropomyosin is out of the way, the troponin has changed its shape, and voila, they touch. Boom. And effectively, I'm not worried about what makes it stronger. It fires the power stroke. So attachment is part 1, stroke is part 2, release with the ATP is part 3, and lastly, reactivating or recocking the head, as I describe it, is step 4. And this will continue to occur, again, as long as the calcium's in there. And again, that's the difference between moving it a little, moving it a lot, putting in more and more units, rather lifting something very nice and light or something really heavy. That's what happens. And that's why I love that animation at the end. You can see the attaching and detaching, but because they're offset, sort of, placed not all in the same, they're not all detaching at once and then reattaching. That way, because of the elastic nature of the muscle, if they all detach at once, we go back to a starting point. And so about half of them stay attached, and half detach, fire, then the next group, and so on and so on. So you'll have something called, again, like climbing a rope. You got one hand on, if not, boom. And they get pulled closer to the midline. And obviously, like any other thing, there's a physiological limit. And that was all that they were showing. And it resets back to normal. Voila. That's the whole idea. What understanding of this helps you understand some really important processes. So really, this is the conclusion of how an individual muscle fiber cell and its components, the sarcomeres, shorten and produce contraction. The concept of understanding preload plays a pivotal role in something that's really significant forensically, and that is being able to estimate things like time of death. And this is because of phenomena, because all your muscles are ready to contract at any given time, if you're not using them, is this rigor mortis, rigidity upon death. And as you can see, it occurs roughly 3 to 4 hours after death. Your brain's not sending any more signals to contract, but the muscles are ready to go. Effectively, that sarcoplasmic reticulum, those terminal cisternae filled with ionic calcium, let loose because they begin to deteriorate. And the calcium then floods the interior of the cell and will under typical circumstances, lead to a peak rigidity, hence stiffness. And why you listen to old shows, probably politically incorrect. He or she is a stiff. We found a stiff. Did you ever hear that expression for a dead person? You didn't hear about Woodstock, so you're excused. Did anybody else hear that? The old crime shows? We found the stiff. Okay. That's what humor me one day. Go to an old Humphrey Bogart movie from the 40s. Okay. There's some really good movies. It's just black and white. You'll get used to it. They'll use that terminology, but I digress. So what happens at a crime scene, whoever is the criminalist or the forensic or the coroner will examine it. They'll look at the ambient temperature, they'll check the temperature of the body, and they'll see if there's rigidity or if rigidity has finally disappeared. That will give them an idea. What makes it disappear, again, it's going to stay stiff for a period of time because, again, there's no more ATP that's going to be made to detach it. What happens then is the proteins of the muscle itself begin to deteriorate, and eventually it becomes flail and begins to start to decompose. And that, obviously, the warmer it is, the faster that process. The colder it is, the less that process. That's why if you ever get an opportunity to see a autopsy, what they're going to do until the remains are being released, particularly if it's involved in a criminal case or they don't know the cause of death, effectively they put them in a refrigerated chamber. In order for a university to be able to do cadaver or cadaver part dissection, you have to have an elaborate set of refrigerators to store those parts, take them out, or they begin to really decompose. They're bad enough, smelly, if you know what you're talking about. I mean, it's a rather elaborate process if you did not know. And I mean, most small universities do not have that capability. Typically, school with medical school. I mean, they had one I taught for a while at IUP when I was just part-timing. They had one cadaver there, and it was only for the pre-med students who would be able to use. So they had a whole setup with refrigeration just for that. Chatham had the same thing, and Chatham's fairly small, like our size. Maybe actually a little bit smaller, but has a lot of funding. It's been around for a long time. Nevertheless, so the intracellular calcium, it lets loose because, okay, ATP is no longer being synthesized, so the calcium cannot be pumped back in, and so the cross bridge forms, but they can't detach, right? And so it results in the myosin staying bound until eventually the muscle proteins itself breaks down. That's rigor mortis, and it's rarely understood. If you did not know, another thing that can pinpoint time of death, if they can get stuck, when somebody ate stomach contents. But certain things take longer to decompose in the stomach. That can do it. And then the other thing, interesting, these are terms you might hear, depending on where you're of interest. Another one's called lividity patterns. It's also known as liver mortis. I don't know if it has anything to do with the liver, but it's a discoloration. Your blood, as soon as you die, okay, if you died in your sleep and you're on your back, what they would begin to see in the skin in the back and the buttocks is this degree of discoloration that would form. It's called the lividity pattern. That's how you know if the body's been moved. Okay, if they see that pattern on the back and the buttocks, and somebody's on their tummy, somebody moved the body. Now, I mean, if that happened at home and you said we would try to roll grandma over or grandpa over to see if there was anything going on, okay, then there's an explanation, and that's where the forensics are very, very interesting. I do not know if we have anything. We may have something on that, but a lot of schools into it. Duquesne has a lot of that because there were a lot of their funding and a lot of their endorsement came from a very recently deceased, one of the most famous pathologist coroners in the country, a doctor named Cyril Wecht, who was actually in the Kennedy assassination. Do you remember that about the President Kennedy assassination? God bless. I'm sorry to pick on you, but he was so important and so well known. He was one of the ones that they had look at to see if this was the single shooter and all the theories that evolved around the Kennedy assassination. Just to give you some context. I knew Dr. Wecht in passing because when I was on staff here, he was the head of he was the president of our medical staff. At the hospital that's now where the Penguins play, they built a hospital. They broke down a hospital and built it on top, called St. Francis Central. Moving on. So that's something you should at least be familiar with, rigor mortis, when it occurs, and what causes it to occur. That's why I'm making a deal out of it. That's most of what we're covering, but I did want to introduce the next stuff That's why I sent you the next PowerPoint sequence. That's B, that's here. I'm gonna make me look good. And this has to, and this is kind of where we are. I'm just doing some introductory stuff for you. I've been trying to do this by intent to limit too much material in each lecture and try to just highlight the important stuff, because I feel maybe that's, remember I said, if my students are having trouble, I have to think of what I'm doing too. I'm not that person who says, oh, they're not studying, they're not working hard at it, they're not very smart. I mean, that's rude to students, because my presumption, everybody's working their butt off. So I was going to say another word. So it doesn't matter. Looking at that fiber, looking at that sarcomere, that's the same that happens everywhere. And so when we contract, okay, it produces the very notion of me trying to do this. Before I can lift up that cell phone, before I can lift up this, I'm telling my muscles, start to contract this process. They don't, the contraction and motion are not the same thing. So basically we start developing tension. The start of that process where the sarcomeres begin to shorten develops a kind of tension or force. That force mechanically has to overcome the load. If it's a very light load, it moves fairly easily. If it was something very heavy, I can't lift this obviously, but if I was going to move one of those components of the tables that are there, you've got to exert a fair amount of force. Probably take two of us to move it, to move it where we want it to move. Okay? That's sort of what I'm driving at here. So initially, every muscle starts just by increasing tension. It doesn't shorten. So iso means same, metric means length. So every muscle starts isometrically, meaning the length doesn't change until it can overcome what it has to lift or move, the load. It just develops tension. So you have no shortening, same length, but the tension increases. Once theoretically, and a lot of this is laboratory based, the next thing, when you move your muscle, once you overcome the load, it moves isotonically. You've developed enough tension to move it, but now you're going to just be shortening the muscle, the contraction. So we call that isotonic, the same tension. That's the distinction. Exercise science is light years different from back when we had in high school and in college, and the trainers and the stuff they were doing to today, the kind of ways that when we were in gym class in high school or at grammar school, how you loosened up and all the things, the jumping jacks, all that kind of stuff, squat thrusts. Everything changes. Okay, one of the exercises that I don't know if they're still utilized today, okay, isometrics. There was a whole way. I mean, it was though you didn't have apparatus at hand. You could exercise by basically pushing against an immovable object. That was called isometric. If you had the luxury of having weights or equipment, and we didn't have any of the elaborate equipments you would have at here, like we go to Planet Fitness, any of the stuff that's there. Obviously, have free weights. They're there, but all the apparatus. Okay, once you start to use that, now you're doing more isotonics. Typically, it would be a mixture of those types of things. The same thing with warm-ups. We went through being jumping jacks, what's called ballistic jumping activity. Oh, that's no good. And doing static stretching. Okay, and now all of a sudden Pilates, maybe 20 or 25 years ago, became a big thing. And all of those types of stuff that are there. I mean, there was all sorts of different activities. I do not know what the state of the art is. When I was treating patients, I knew a lot better, but I haven't treated patients for 20 years. So I was a little more familiar. And that's part of the things, depending on your field, those are the types of things we would keep up with. This is what seminars and conferences and meetings are about, and continuing education. That whole continuing education thing, for most of you, get used to it. But once you get out of here, the merry-go-round is just started. I keep learning. I love that stuff. So that's sort of what it is. So force and duration of contraction vary about the frequencies and intensities. What you're going to learn, and the take-home point from this going forward is mostly in the muscle system and particularly in the nervous system, frequency equals amplitude. When I yell, that wasn't volume, that was frequency. Your brain interprets it as frequency. Rather than if I'm speaking softly, it's like this. When I'm yelling, it's. And that's true for hearing, that's true for things that startle you visually. Frequency equals amplitude. For pain, same thing. And the same thing for muscles. You're going to see the more what we're going to do. And muscles are a little bit different because we reach, remember, there's a limit at how much that muscle can contract. So you're going to see that it is not quite the same. And a lot of this comes from what we used to do. And I know it is still, we use a lot of electrical stimulation and rehabilitation for muscle injuries. Those of you who are in athletics or enjoy athletics, either recreationally or do so here at the university as either a club or an interscholastic activity. When you have damage, electrical stim has been around for a very, very long time. And this is what we learn when we diagnose things. We use what's called an electromyography or EMG. So we're stimulating the muscle scientifically to not only diagnose it, but to treat it. This is part of when somebody had a carpal tunnel, this is the way we would do it. When somebody has, a back and maybe they need to have surgery from a sciatic nerve impingement, this is how it's done. It's done by assessing a variety of things, not just MRIs and CTs, but also electromyographic evidence. The nerve, each nerve contains axons with hundreds of motor neurons. I mean, it can be as little, and you're going to see that. They branch into those terminals. That's what we've been talking about, the terminals. And what we have been really studying is an individual motor unit where the nerve meets the muscle. That's about as much as I'm going to ask you about motor units. So the motor neuron and all of the fibers, the smaller the fiber, the greater the control. So what you're going to see, you're going to have typically, if we're using fine motions facially, the distinction between this or this or this, or fine movements, very few motor units are involved. Big muscles just to help you stand or kind of hold things in place. We call postural muscles. They serve hundreds. So muscle fibers from motor unit are spread out, so the stimulation of a single point only causes a weak contraction. And if we need more to lift something heavier still, we recruit or bring more to the party. This is what it kind of means. Here's your standard spinal cord. Coming out of this is the gray matter, is the ventral horn. You might remember that. And you have multiple, this is the motor nerve portion. And you can see it going to, and they're just demonstrating with two. This is what I meant when you saw that neuromuscular junction. They almost like little rounded projections, almost like feet sitting on different areas. And so, I mean, it was a very good, the animation reflected the true anatomy, nerve, the motor end units, etc. And here, these are all individual fibers that they're coming to. And this is where the lab comes in. The rate determining step on how rapidly a muscle fires, and so too how rapidly it relaxes, has to do with the chemicals, that neuromuscular junction. Understand that this is an electrical system that communicates with the muscle by chemicals. The same thing in your nervous system. One nerve talks to the other and releasing chemicals. There's a process you're going to see, there's a delay that you're going to see called a latent period. I mean, the next time you have a case, maybe you have a friend or a relative who's across the country, maybe down in the South, maybe have relatives down in Florida who retired there, or Texas or Arizona, and you and I are talking to them in real time. That's electrical energy. For us to get there, we can't get there like this. It's not like in a sci-fi movie. We don't have electric transporters that'll magically get us there instantaneously. We're going to have to get in a plane that flies, 500, 600. It's going to take, if I want to go to California, it's going to take 4 or 5 hours. We're about 2,500 miles away, right? That's the idea. Yet we can talk to them in real time. Literally not just around the country, but around the globe. So Understand that the rate determining step, which we say in science a lot and in chemistry, has to do with how rapidly those neurotransmitters are released and how effective they are at causing, in this case, that muscle to contract or twitch. So the switch is something we only see. We do it in the lab because we rehab muscles with this electrical stimulation. We diagnose them. Okay, the muscle fiber contracts quickly, then relaxes. And this is the myogram, and the fancy acronym you'll see is called EMG, electromyography. And we have a tracing, as you can see visualized on the computer. And I'll start with this when we get back, but this is kind of what it looks like. You have that latent period, chemical getting across, fires rapidly, releases more slowly. And notice we're in milliseconds. This is a period for that to get across 2 to 3, 5 thousandths of a second. In nerves, the time nerve to nerve would be even faster. We're probably talking in microseconds, not thousandths of a second, but milliseconds. I'll leave you with that. See everybody. We'll go back to this on Friday. Focus on, obviously, on the exam and things like that. Thank you.